This is Mr. Wilson again with a waves review video. Are you ready? We're getting towards the end. So, on your review packet, if you turn to, if you're following along, 67, talking about waves. Waves, energy moves in waves. There's this cool song on Bill Nye, if you look up on YouTube. Ooh, energy moves in waves. Anyway, so we've got energy moves in waves. If you are at a stadium, you start off in section 101 and the wave goes by. You don't end up in section 108 because energy moves by, potential and kinetic as you move back down, but you don't move mass. Energy moves in waves, not mass. That's the first thing. Second thing is there's a bunch of definitions here. Frequency, period, amplitude, crest, trough, wavelength node, antinode, in phase, out of phase, coherent, incoherent, monochromatic. Basically look those up because you're going to need to know those definitions. Transverse waves is what I'm going to do next. Transverse wave is a typical type of wave. For instance, say you have a boat and your boat's right here, got a little tugboat, doot, doot, doot. And when the wave goes by, the wave velocity goes by, that boat is only going to move up and down. Do you believe that? You should, because it's only going to be able to move this way. It's not going to move very much this way or that way. We're not talking surfing, we're kind of talking open ocean, open lake, where it just moves up and down. And if you remember, transverse waves, transverse, when you think about it, capital T for transverse, it's like an upside down perpendicular sign. So what happens is the boat will move up and down while the velocity goes this way. It can only move up and down. So transverse wave, that's the thing there. Light is an example. Most waves are transverse waves, I should say. Light, any electromagnetic wave on the electromagnetic spectrum, X-rays, gamma rays, radio, all those good waves, microwaves. Light, electromagnetic waves. We're talking about, like I said, X-rays would be an example of an electromagnetic wave. So those are, or water waves too, let's include that. They would be transverse waves. Next we have, oh, I don't have an eraser. There's one, hold on. So waves don't move mass, they move energy. Transverse wave is the first one. Longitudinal is the other main example. Longitudinal wave, the two L's are like perpendicular, or not like perpendicular, excuse me, parallel signs. So if you think about like a speaker, for instance, okay, you got a big subwoofer, you know, that kind of bass sound. It'll compress the air molecules. When it goes out, so it moves back and forth like this. If you picture a big subwoofer going, you know, back and forth that way. This will compress. That'll be a compression. And then you have an expansion. And then you have a compression. An expansion. If you were inside the air, or inside this wave where the air is being moved around, you're going to move back and forth like this when the wave goes by. So if the wave velocity is this way, you're going to be tossed side to side. So notice how those two are parallel to one another. When this wave goes by, the particles are going to go sideways. Sound is the main example, and sound needs a medium. Sound needs air or something to move. It's a mechanical wave. So sound is an example of a longitudinal wave. Longitudinal, parallel, whoop, 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 whoop. So remember that kind of movement right there. And go through here, number 71. ART tells you about what happens to waves when they reach a new boundary. Some of the energy is absorbed. Think about like light going into water. Some of the energy is going to be absorbed. Some will be reflected. And what angle it comes in at, the angle of incidence. Let me just draw that real quick. So ART we're talking. Some is absorbed, some of the energy. Some is reflected. And by the way, the amplitude would go down a little bit because the energy is absorbed and the energy depends on the amplitude. Some is reflected and some is transmitted. And the part that's transmitted, especially with light, can be bent or refracted. So, you've got air and some agua. If we have some light coming in here, the light's going to come down here. When it gets into the water, it's going to slow down and go toward the normal, slow tow. And remember, the opposite one is run away. Run away! So when it slows down, it goes toward the normal. Remember, this is your angle of incidence, this is your angle of refraction. N1 sine of theta 1 equals N2 sine of theta 2. Remember, that's Snell's law. You need to know how to work with that. N1 would be 1, because material number 1 is air. In this case, material number 2 is water, because it ends in water. N equals 1.33. N2 is 1.33 for water. And then you plug in here, you need to work with degree mode on the calculator, of course. That's degree on a perspirant that I was pretending to use there. Also, if you were to look at the wavelength, what do you think is going to happen to the wavelength when it gets into the new medium and slows down? Is it going to change? Yes, it is. It's going to be shorter. So it'll be shorter like that because it's going to compress. Just like if you were diving into the water, you would compress your body length a little bit because, you know, you're almost like a slinky person if you picture it, because you have this spinal column. And so it compresses and pushes them closer together. Also, reflection is one where the angle of incidence right here is going to equal the angle of reflection. So this is reflection bouncing. This is refraction bending. That's the end of Waves 1. Thank you very much.